All right, so today is our very last lesson of the school year, 9.4 Geometric Sequences and Series. This is where our Algebra 2 curriculum will be ending this year. So bittersweet that I don't get to teach this to you in person, but hopefully this video will suffice. If not, please, 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 like always, let me know if you have any questions or anything I can do to support you. So let's get started. Our objectives for today are to define geometric sequences. We're going to find the terms of a geometric sequence and then find the sum of a geometric series. So first, let's define what is it. So we know a sequence from past lessons is a list of numbers that have a pattern that connects them to get from one number to the next. A geometric sequence is a sequence in which the ratio of the successive terms is a constant called the common ratio R. All right. So in other words, to get from one number to the next, we're multiplying or dividing by something. And that number that we're multiplying or dividing by is called our common ratio R. This is very comparable to an exponential function. So we talked about this in 9.1's lesson. We went through an example problem where it did not have a common first difference, so it wasn't linear, or what we've now learned to be arithmetic. But it had a common ratio. When we divided our numbers together, we got the same number every single time. An example of an exponential equation or function is something like this, where x is our variable, is our exponent. So example 1, let's just look at identifying if something is if something is geometric or not. So looking at the first one. Well, in the directions it says determine if it could be arithmetic or geometric. So we're going to go through both just to make sure it's one or the other or neither. So 100, going from 100 to 93 is subtracting 7. 93 to 86 is subtracting 7, and 86 to 79 is subtracting 7. So here you have a common difference, making it arithmetic. So this one's not geometric. Let's look at the next one. 180 to 90 is subtracting 90. 90 to 60 is subtracting 30. And 60 to 15 is subtracting 15. From here, we got, hang on. Nope, that should say 45. There we go. Okay, sorry. A little minor hiccup in the mental math there. So it'd be subtracting 45 to get from 60 to 15. So it's not linear, meaning it's not arithmetic. We don't have a common difference. So now let's move on to our next thing, the new thing, which is geometric. So to find or identify if we have a common ratio, we're going to start with the end of our sequence here, 15, and divide by the number that comes before it, so 60. So 15 divided by 60, which I don't have that math done right offhand. We get that it's 0.25. Then we do 60 divided by 90. And we get 0.67. That's rounded. Well, they don't match. I could go through and do this again and do 90 divided by 180, but it's not going to make a difference because in order for something to be constant, it needs to be the same number, and they're not the same numbers. So, it's not arithmetic and it's not geometric, so we're just going to say none. Looking at the last one. Right off the bat, it's pretty clear that this is not arithmetic because to get from 5 to 1 is subtracting 4, and to get from 1 to 0.2 is subtracting 0.8, and those are not the same number, so it's not arithmetic. Let's go through and check to see if it's geometric. So starting with the n, so 0.04, dividing it by the number that came before it, 0.2, we get 0.2. Taking 0.2 and dividing it by 1, we get 0.2, and taking 1 and dividing it by 5, and we get 0.2. So you can see here that we keep getting the same number when we're dividing these values. We keep getting 0.2s, making it geometric because we have a common ratio. So, just like with arithmetic, we have a general rule for a geometric sequence. It also relies on knowing a sub 1 and here knowing your common ratio. And again, n is still standing for your term number. So example 2, we want to find the 7th term of the geometric sequence. We have two problems here. You could go through and find your common ratio and then keep multiplying by that number to get to your 7th term, and that would be perfectly fine. Or you can use that general rule that we defined on the last slide. I'm going to use the general rule just to show you how it works, but you could use either method. So the general rule, a sub n equals a sub 1 times r to the power of n minus 1. Now this might look pretty familiar to something I already walked you through in 9.1's lesson, and now this has just become much more formalized and defined. So in order to write this general rule for a geometric sequence, we need to know the common ratio, r. We're told that these are geometric, so you don't need to go through and divide all the numbers, just divide 2 of them. So I'm going to take 12 divided by 3, and that's 4. That tells me to get from one number to the next, I'm multiplying by 4. So a sub n equals a sub 1, which is 3, times 4 to the power of n minus 1. So my general rule or expression to represent this list of numbers is 3 times 4 to the power of n minus 1. Now to apply that and find the 7th term, I'm going to plug 7 in for n. So I'm doing 3 times 4 to the power of 6. And that's going to give me 12,288. You could have just taken this list and continued from 192 multiplying by 4 until you get to the 7th term. That would have worked as well. So I would take a moment, pause the video, see if you can work on the next problem, and then press play when you're ready to see the answer. All right. We have 0.001 as our first term, 0.01 as our second term. I'm going to do a little bit of division here to find my common ratio. And I find that it's 10. My first term is 0.001 for a value. My common ratio is 10. So I end up with this setup of 0.001 times 10 to the power of n minus 1. I'm going to use that to now find my 7th term, plugging 7 in for n. So I'm doing 0.001 times 10 to the power of 6, which gives me 1,000. You could have also found the 7th term by continuing where this sequence had left off and multiplying by 10.